Well, hello again, class. We're doing Module 12, starting Module 12 today, and specifically that is Chapter 10, Hypothesis Testing, where we really get into some of the deeper levels of just what we can do with statistics. There's a danger here that we treat this too deeply, that we just kind of lose all concept of what's going on. And then you get to the homework and you think it's too impossible to do. Or we start out too easy, because really when it comes down to it, the math involved in this chapter, when we use StatCrunch, really isn't all that difficult. But there's two hypothesis tests we're going to do in this chapter. There are about 5 or 6 more that we have. So in order to keep them all straight in our mind, it's a line that we walk to make sure we know just what hypothesis testing is, so that we can synthesize all those other tests into our head well. So the first thing we're going to talk about is the language of hypothesis testing. And you know, when we're doing statistical research, really we're comparing one thing to another. Maybe the one thing is an assumption, and the other is sample data that we take. What we think the population is this, so we take sample data and see if they are the same. But we know that they are never going to match, and we've alluded to this the entire semester long. They're never, in practicality, going to match, but will they match enough? Will they match enough to be considered the same? And where is that threshold of, well, now they no longer match? And we've kind of gotten the idea that sample size matters. We have to make sure that we have enough room on either side of the normal curve for the tails, and all that kind of stuff. All that stuff now comes into play, and hypothesis testing takes all of it into account to decide if the mismatched things are just the probability of two things that are the same being a little bit different, or the realization that two things just aren't the same, and to have some tools to really determine that. And again, technology is going to hold almost all of it, but it comes down to Z and T scores. If we standardize things well using either the normal curve or the student's curve, we get Z or T scores. And we see where those Z and T scores are. If we are, I don't know, say 2 standard Z scores and T scores, standard deviations, right? If we are 2 standard deviations away, isn't that kind of unusual? So if we're less than whatever this boundary is, if we're maybe only a half or 1 standard deviation away, well, that's okay. That's probably normally expected. But if we're 2 or 3 or 4 standard deviations away, then we know that we're no longer talking about the same thing. So that's what we're doing. We're just representing how many standard deviations we are away from another, and that is it. We'll make it a little bit more precise than that, but don't lose sight on what we just talked about in the previous slide. So we have these things called hypotheses, hypothesis testing. We have 2 hypotheses that we're going to work through, and the hypothesis is a statement regarding a characteristic of one or more populations, and it is stated as a fact. It's not, I wonder if, it's this is the way the population thinks. We state it as a fact, and then we determine whether or not that hypothesis is true or false, similar to all the different hypotheses you've ever worked through in your science classes. So let's talk about, here's 3 examples, and we'll revisit these samples throughout this PowerPoint. Let's say that in 2008, 62% of American adults regularly volunteered their time for charity work. That is an established statistical number. But here, this underlying portion is a hypothesis. A researcher believes this percentage is different today. She no longer thinks that it's 62%. The next situation, according to a study published in March 2006, the average length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. Maybe it's because everyone's got phones, and you used to have to pay per minute. How many of you remember those those cell phones where you bought minutes, where you'd be looking at the timer and you'd have to hang up before it reached the next minute. Well, that no longer is there. So the researcher thinks that maybe because calling is unlimited, they have increased. Using an old manufacturing process, the standard deviation of the amount of soda put in a bottle was 0.23 ounces. 16-ounce bottle, 20-ounce bottle, give or take a little bit, right? Well, there's been some new equipment, so the quality control manager believes the standard deviation has decreased. Again, these are three statements. They are either true or false, but they are statements, and those are some hypotheses that we have. So this is what we have in our steps to hypothesis testing. We're going to make a statement regarding the nature of a population. We're going to collect evidence to test that statement. We're going to analyze the data to assess the plausibility of that statement. I think it has changed. Let me collect some evidence. The evidence is different than the assumption. Is it different enough? I'll do some analysis and decide that, oh, you know what? Based on my collection of data, it turns out that my original hypothesis here is bunk. This is, or whatever we decide. And that's what we have. So there are two hypotheses. There's a null and alternative hypothesis. The null hypothesis, denoted H sub 0 or H naught, is a statement to be tested. It is the statement of equality, no change, no effect, no difference. It's always going to be the null hypothesis equals this. Data is going to be collected to determine if this hypothesis should be rejected as false. The alternative hypothesis, denoted H sub 1, is, or in some places I've seen, I think StatCrunch says H sub A as alternative. The alternative hypothesis, denoted H sub 1, is a statement that we're trying to find evidence to support. Maybe the underlying statements 2 slides ago. We think it is now this. The standard deviation was 0.23. That's the null hypothesis. The standard deviation equals 0.23. The researcher thinks it is now different. It is less than 0.23. And that's where they're trying to find evidence to support. Okay, so there are three types of ways to set these up in this chapter. Here are 3 normal curves. We have, I probably did it backwards. Equal versus not equal. Two-tailed test, a left-tailed test, and a right-tailed test. Let's say that the researcher doesn't know if it's increased or decreased. The researcher just thinks that things are different. Well, that means the z-score that we find with the collected data is going to possibly be found either in this tail or this tail. Well, let's say the researcher really thinks that the statistic has decreased. That means that it's going to be found in the left tail. Or let's say the researcher thinks the average length of a phone call has increased. So the z-score is going to be found in the right tail. So that is what we have. We have either the parameter h naught, the null hypothesis, either the parameter equals some value, or the alternative hypothesis is that it doesn't equal that. The left tail test, the parameter equals some value. The researcher perhaps thinks that it has gone down. Equal versus equal some value, maybe it has gone up. So those are our 3 different scenarios for our 2 hypotheses. So for each of the following claims, let's determine the null and alternative hypothesis and whether it's two-tailed, left-tailed, or right-tailed. And I think I'll just put all 3 of them up at once. Here's our first example with the 62% of Americans. That it's different today. Different, that's your key. Not less than, not greater than, but different. This is dealing with a proportion P. So our null hypothesis is going to be P equals 0.62 because that's what it was. That is the statement of no change. Nothing has changed. We're stating this right now. Nothing has changed. The proportion is still 0.62 just like it was. And the researcher is now thinking, I don't agree with that status quo, that no change. I think it is different. So that is the alternative hypothesis. And because not equal, the researcher isn't claiming that it's more than 62% or less than 62%. It's just claiming that it is different. Okay? How about this one? Let me go all three. This is the cell phone. The researcher thinks the mean length of a call has increased since then. Well, because this is a population mean, then the null hypothesis says the mean equals 3.25. Nothing has changed. I don't care what the research might lead to now. It was that in 2006. It's still going to be that today. The researcher doesn't believe that. The researcher believes the length has increased. So the alternative hypothesis is instead of mu equals 3.25, its mu is greater than 3.25. And because it's greater than, he's expecting or she's expecting that z-score to be greater into the right tail as a greater than. And our last one, as you can probably imagine, it's the same idea. The soda, 0.23 ounces, the quality control manager believes the standard deviation is decreased. Well, sigma equals 0.23, or sigma is less than 0.23, which would be a left-tailed test. So that is this idea of the stating those null and alternative hypotheses. Now we're going to talk about the conclusions. Once we have done the test, we have a conclusion to make. And what does the evidence show? Well, the researcher is looking for statistically significant evidence. Statistically significant evidence is evidence to show that what was once assumed to be true is now no longer true. If that evidence is found, the researcher is going to reject the null hypothesis. The null hypothesis was average length of a phone call is 3.25 minutes. We found statistically significant evidence to show that that should be rejected, so we reject it. Well, the flip side of that, you'd think that the opposite of reject is accept, but it's not. It's not. If the evidence is not found, if we don't find any evidence to reject the null hypothesis, we have to say we have failed to reject. And there's a reason for that. It goes back to this, and I have to be honest, I never thought about this guilty versus not guilty thing until I saw this as an example. You never hear in whether it's a crime show or a movie, or if you've ever been in court, whatever, you never hear the defendant declared innocent. They're simply declared not guilty. And the reason for that is we may not find any reason to say guilty, but just because the prosecutor didn't find any or enough evidence to say the defendant is guilty, does that mean the defendant is innocent? No, it just means that the prosecutor didn't find enough evidence to show beyond a reasonable doubt that he was guilty. So because we cannot declare or find clear proof to declare someone's innocence, all we can do is say the defendant is not guilty. And the same idea with this null hypothesis. The null hypothesis says the average length of a phone call is 3.25 minutes. Well, we took a sample and found that it's greater than that now. Yes, then if we found that it's greater than that, then we can say reject. What if we find evidence to say that it's the same? Well, just because we found evidence to say that it's the same doesn't mean someone else might not find evidence to say that it's not. So we can only talk about the evidence that we find. We can never say with certainty that something is innocent or worthy to be accepted. We can only say that it is rejected or failed to reject. And it's a little confusing as you go. Hopefully will make sense as we go. Back to the 3.25 minutes. Suppose the sample evidence indicates that the null hypothesis should be rejected. Well, then the conclusion could be this. There is sufficient evidence to reject the null hypothesis, so we will reject it. The mean length of a phone call is greater than 3.25 minutes. That is our conclusion. And what about if what if we collected sample evidence that says the null hypothesis should not be rejected? How do you word that? Well, there is insufficient evidence to reject the null hypothesis, so we will fail to reject it. The evidence that we found is consistent with the mean length of a phone call equaling 3.25. We're not saying it is 3.25, we're simply saying that it is consistent with the average length being 3.25. Okay, so now we move into errors. We know there's always going to be errors in collecting statistics. Not errors because we've made a mistake, but just because when you collect data, it's never going to match what is established, or even if you take two samples, they're never going to match each other. That word error is what that difference implies. So there are two different types of errors we have. The reality about a population is out there. We may not know it, but it is there. Let's just say, for the sake of discussion though, that we can find definitive proof about the nature of a population. Maybe it's the US Mint says the weight of pennies is this, and that is an absolute established fact. And then some pennies weigh more than that, some pennies weigh less than that, because they've either been worn out or because the process has a standard deviation built in. But let's say that we can find that definitive proof. Then we do our research and we decide whether or not we should accept the definitive proof or not. Okay? And there are 4 different outcomes. So let your, maybe even pause to get your brain wrapped around this. But there are 2 realities. Either the basic assumption at the beginning, the null hypothesis, is true or it's false. The reality is it's either true or it's false. And then the researcher made a decision to either reject the null or fail to reject the null. You could pretend this said accept, but we're not allowed to, right? The decision was made, I'm going to accept the null as true, I'm going to reject the null as false. So now let's see how those match up. Can you see that if you fail to reject, if you accept the null and the null is true, that's a good thing. What if you decide to reject the null and it turns out that the null is false? That's a good thing. The trouble comes in if the reality is actually true, but we've rejected it. We shouldn't have done that. We shouldn't reject the true reality. And that's probably because we chose an alpha that's too big. Hang on to that statement. I'll show you some pictures in a minute. We probably picked an alpha that was too big. Or the other error could be where the reality is actually false, but we chose not to reject that. And maybe that's because our alpha was too small. So those are our 2 errors. The level of significance is what we consider to be unusual. Typically it's been 5%, right? If something happens in that 5%, or the likelihood is 5%, then that's just too small. That's probably not reality. We've chosen the 10%, 5%, or 1%. It could be any value. Does it make sense that if this is too big or too small, we could end up making some errors based on that? Let's look at the type 1 error, where our alpha is too big. Here is the population. Here is the sample that we took. We took a sample and found a z-score that was a fair bit away from the population middle. Now this looks like it's pretty far away, but if we have an alpha value that's substantially big enough, then it looks like it is in, okay, maybe I made mistakes a little backwards. The z-score is a certain distance away. If our alpha zone of unusual is too large, then we may end up rejecting this one when we shouldn't reject it. And let me show you the the type 2 error. If here is our z-score and our alpha rejection zone is too small, we can see that this z is going to be in the OK zone, and that we would accept this, fail to reject it when we should have rejected it. So if I go back and forth between those two, again, right here, we can see that because I made my rejection zone very large, it's going to make us reject all kinds of things. And here, because my rejection zone is so small, it may keep me from rejecting things that I should have rejected. And so some of you are wondering, well, then how do you know what alpha to pick? And is it conceivable to think that some researchers out there want something to be rejected, do the analysis, find out that they have to fail to reject it, so they just change their alpha size to make it so they're allowed to reject? I don't know. I do know that depending on whether you are in humanities, soft sciences, as opposed to some hard sciences, your alpha may be more inclined to be smaller or larger. And I'll let future stats courses, future research type things talk about that. There isn't a whole lot that we talk about in this book. All of the alpha amounts have been given to us within this. So let's see. Okay. So for each of the following claims, by the way, did I say thanks for being here today? For each of the following, what would it take to make a type 1? What would it mean to make a type 2 error? Okay, charity work. Remember this one, 62%? A type 1 error is made if sample evidence leads the researcher to conclude that it's no longer 0.62 when it really still is. Maybe that's because the rejection area was too big. Alpha was too big, which means the z-score that was here, because the rejection area was so big, it caused the researcher to reject the null, even though those numbers were close enough to be the same. A type 2 error is made if the sample evidence leads the researcher to conclude that the proportion is still 0.62, when actually it's different. The z-score was here, but the alpha size was so small that almost nothing is ever going to get rejected. And that led to that type 2 error. I'll gloss over this one. It's basically the same thing. The balance then of, and this is a pretty interesting fact. It may show up as a homework question or a quiz question. The probability of making a type 1 error actually is your alpha. And it's got to be chosen by the researcher before the sample data is collected. So again, the level of significance, alpha, is the probability of making a type 1 error. So if you say your alpha at 5%, there's a 5% chance that you're going to make a type 1 error. If you set it at 0.1, there's a 10% chance you're going to make a type 1 error. And as the probability of a type 1 error increases, well, the probability of making a type 2 error decreases, as you can imagine from the visuals of those slides. Whew! That takes us to the end of section 1. That was a whole lot of weird theory type stuff. Work through the homework in that. The homework does a great job of drilling in what those things are. Make yourself a cheat sheet of those type 1 errors if you don't have a book accessible. And then join me back again for section 10.2.